Alrighty, so next we're going to learn a little bit about acids and bases, and that's going to prepare us to write another kind of double displacement reaction, the acid-base neutralization reaction. So for this course, we really focus on Arrhenius acids. So this is historically the first definition, so it's the least complex of all the definitions. Arrhenius said that an acid is an H plus producer in water. He also defined a base in a similar manner, except a base is going to be a hydroxide ion producer in water. So we need to be a little bit careful here because there's no such thing as H plus. Scientists write H plus all the time, but when we write H plus, we're really thinking about H3O plus. So let me put that in the other notes part. H plus is really H3O plus, which is known as the hydronium ion. H plus, you'll hear people call it a proton, but it just doesn't exist. It would be very stable like that, unstable like that, and so it actually exists as the hydronium ion. What kind of things are going to produce hydronium ions or H plus ions in water? And again, we're using those terms interchangeably. So an example of this would be hydrochloric acid. And it's probably an acid that you've encountered even in lab thus far. Bases, most common base that we use in lab would be sodium hydroxide. So we're going to approach this the same way we approached our precipitation reactions. We're going to take the H plus, the hydrochloric acid, and divide it into H plus and Cl minus. We're going to take our sodium hydroxide and divide that into Na plus, or split it into Na plus and OH minus. They're going to do-si-do. It's a double displacement reaction. Remember, in the middle there, we got to reorder it. So the cation comes first. So one thing that will be formed is NaCl, which you'll look at your solubility rules, right? It's aqueous, it's got a group 1 in it. And then you have H plus hooking up with OH minus. So HOH. But we don't write it like that, right? That's H2O, that's water. When you have an acid-base reaction and you form water as a product, you're going to label that as a liquid. Liquids work the same way that the solids work in the precipitation reactions. Those ions are in love. They're stuck together now and they're not going to disassociate no matter what. Whereas this, in the water, we expect the sodium and the chloride, because it's aqueous, to not be together at all. They're just floating around individually. All right, so this is going to be the trend for any Arrhenius acid and any Arrhenius base. They're always going to produce water when you mix them together. So under other notes, I usually put that an Arrhenius acid plus an Arrhenius base will produce water and some kind of salt. This is known as an acid-base neutralization reaction. Very predictable. Alrighty, so let's talk about the Bronsted-Lowry theory of acids and bases. It's slightly more complex than the Arrhenius one, but it's not too bad. So Bronsted-Lowry said that acids are H plus donors. That kind of falls in line with this. So we can use the same examples like hydrochloric acid or nitric acid, any of those common acids that we're used to that'll split into H plus and an anion. The base is where it gets a little bit wonky. Bronsted-Lowry said that a base was an H plus acceptor. There's so many examples out there. For my CHEM100 students, I primarily want you to be aware of the fact that ammonia, NH3, is a Bronsted-Lowry base. And let's look at why. Here we have hydrochloric acid. I'm going to draw it as a Lewis dot structure. So this line in the middle is a bond, and it represents shared electrons. You're going to learn how to draw the Lewis dot structures in a couple weeks here. But for now, I just want to give you some insight into how ammonia acts as an H plus acceptor. Ammonia has some extra electrons on top. So these two dots that you see right there, these are electrons. They're known as a lone pair. So the electrons have the ability, this lone pair of electrons, they have the ability to come and grab the H plus from the chlorine. These shared electrons fall back onto the chlorine. So if NH3, if ammonia, picks up an extra hydrogen, what do you think it forms? You all know this polyatomic ion, it's ammonium. And then we have chlorine with some extra electrons, so it becomes Cl minus. There's other examples of Bronsted-Lowry bases that you'll run across. Typically, they're going to have a negative charge. So something like sulfate picks up an H plus and becomes hydrogen sulfate. So apart from ammonia, look for species with any kind of negative charge, because that puts it in a position to pick up the H plus. At the end of the day though, the one that you'll see on a test, or you'll see on a quiz, is the ammonia. That's the one that I want you all to know from this Bronsted-Lowry category. So it's important to be able to identify species as either an acid or a base, especially when you need to predict the products, because we need to know, is it going to do an acid-base neutralization reaction, or is it going to do another type of reaction, like a precipitation reaction? So you want to feel confident identifying your acids and bases. We're going to practice that a little bit here. So which of the following are bases? So we talked extensively about ammonia, and that's definitely one of the bases here. Do you recognize any other bases? So I hope that the OH here reminded you of the Arrhenius definition of a base, an OH minus producer. So we know that this would break into lithium plus 1 and OH minus 1. The fact that it produces the hydroxide makes it a base. Any other candidates? So we're definitely not going to classify this as a base, because when it breaks up, it breaks into H plus and Cn minus. it doesn't produce OH minus. So I'm sure you're sitting there and kind of yelling at your computer screen, well, what about letter F? I see the OH in letter F. Doesn't that act like a base? So we have to be really careful. The difference between letter F and letter E is the fact that E is ionic. When you have an ionic compound, there's no doubt that it will split up. So we have a metal plus a non-metal. And they have the capacity to dissociate from one another when you mix them with water. So in the solid form, they're together, but once you mix them with water, they tend to go their separate ways. When you have a covalent compound, because they're sharing those electrons, it usually doesn't dissociate. There are exceptions, such as strong acids, but as a general rule of thumb, covalent compounds stay whole in water. They don't form ions like our ionic compounds. So the consequence of this is that even though there's an OH here, it stays as OH in the compound. And this whole thing stays whole when we mix it with water. The Bronsted-Lowry definition, or the Arrhenius definition, says that a base is an OH minus producer. And if it stays whole, it's not producing that OH minus. Rule takeaway, because I know this can be confusing at times, if you draw something out, or you can ask for a picture of it, if you have OH attached to carbon, then it's not a base. It's going to be one of those tricky ones that you really have to look out for. Let's do some practice here identifying acids now. Some of these species, they should start to jump out at you as having the potential to function as acids. So whenever you see something that you can split into ions, for instance, this first one here, hydrofluoric acid. We know H plus is a thing, and we know F minus is a thing. And the fact that we can split it up into ions and form H plus, that means that it's an acid. Diatomic chlorine? Yeah, I don't know how to split that up. Or even if I try to guess at splitting it up, it definitely isn't forming H plus. So that's not an acid. Down here, we would split it into K plus and OH minus. So this is potassium hydroxide, and this actually functions as a base because it produces OH minus. The hydrogen sulfide that you see over here, that's a tricky example because in the previous problem, or in my earlier discussion, I mentioned that things that are negative have the potential to pick up H plus and function as bases. So this is the hydrogen sulfide acting as a base, acting as an H plus acceptor. However, we also know that it can split into H plus and SO3 2 minus. How do we know that? Well, you have your polyatomic ions memorized and you know that sulfite is a thing. So you're like, I can envision that splitting up like that. So if it were to split up like this, this is the same starting compound acting as an acid. There's a bunch of species out there that can act as an acid or a base. So those are known as amphoteric species. So that's something that acts as an acid or a base. It just depends on the environment. So be on the lookout for those. If you see an H plus that could potentially come off, but at the same time it has a negative charge, then that's a good indication that you're looking at something that's amphoteric. So I'm going to circle this one because it is an acid under the right conditions. All right, so D and F are both acids as well. How are you going to recognize these as being acids? This one I think is one of the trickiest ones, but it's also one of my favorite ones. This is acetic acid, which is vinegar, and that's why it's one of my favorite ones, because I really like pickles and relish and all that good stuff. So because I'm a fan of vinegar, I always ask students about acetic acid. How do you know that it's an acid? It's a weak acid, and that's why you can put your hand in the pickle jar and you're not worried about burns like you would be with hydrochloric acid or something like that. You want to think about the ions that form. So acetic acid splits into acetate, which there's different ways to write the acetate ion, but that's one of the ions that you have to memorize. And then it would also have H+. So the fact that there's an ion associated with it that you had to memorize is a good indication that it has the potential to split up, even though it's covalent. Confusing, I know, kind of, sometimes students just wind up memorizing vinegar because it's such a weird example. Last one, again, knowing those polyatomic ions is key here. We have H+ and nitrate. So definitely acid because we have the H+ forming when the compound dissociates. Alrighty, let's move on to page 4 and talk about how to write acid-base reactions. A couple of things here. One is acid-base reactions fall under the category of double displacement reactions. So the general idea is going to be very similar to what you saw in the precipitation reaction video. It is important that you recognize that you have these couples here, but more specifically, you have couples that produce H+ and OH-. So you also not only seeing a couple, you're seeing an acid and a base. And that makes it a little bit harder, I think, than just the precipitation reactions. All right, so here, just start splitting everybody up. We have H+ and NO3-. I'm using my knowledge of the polyatomic ions to determine how it's going to split up. The fact that it's aqueous as well tells me that it's going to split up. Na+ and OH-. So this is an Arrhenius acid because it's producing H+, and we have an Arrhenius base because it's producing OH-. They're going to do-si-do. So the sodium will hook up with the nitrate, and the H+ will hook up with the OH-. So when H+ and OH- hook up, we get HOH, or water. In these reactions, the water is always going to be followed by the letter L. The letter L stands for a pure liquid. Once in a while, you'll encounter other types of pure liquids, but in general, especially for introductory chemistry courses, water will be the pure liquid that you should look out for. And then sodium hooks up with nitrate. We're going to reorder this so the sodium's first. It's a 1-to-1 ratio. And I get NaNO3. Solubility rules tell me that this will be soluble, so I'll label this as aqueous. You also want to check that it's balanced, and this one happens to be balanced with all coefficients of 1. All right, let's keep on working it. We have a couple that's splitting up into H+ and Br-. And because it's producing H+, I'll call this an acid. And then we have something that's splitting into K+ and OH-. Because it's producing OH-, I'm going to call this a base. H+ hooks up with OH-, that's going to be our water. And then K+ hooks up with Br-. K+ needs to come first though. So we have H2O liquid as one of our products, and the potassium bromide would be our second product. It's aqueous because it has a group 1 cation in it. Again, double check that it's balanced. This one is balanced. Alrighty, let's wrap up these last two problems. We're going to start in the same way. I'm going to split the nitric acid into H+ and NO3-. And I'm going to split the calcium hydroxide into calcium 2+. I know that because it's in group 2. And then hydroxide is just OH-. So if you have a subscript that came from a crisscross, that shouldn't be part of the ion when you're doing your do-si-do part, when you're recombining them. So think of this 2 as going back to calcium. Send it back to where it came from. So put it back up there. Let's recombine everybody. So H+ is going to combine with OH-, and the calcium will combine with the nitrate. I want to take a second here and work through that. So we have Ca2+ and NO3-. Since it's a polyatomic, I'll use parentheses, and I'll bring the 2 down to the outside of the parentheses. And there is this 1 here, but that doesn't do anything. So CaNO3,2. Nitrates are always soluble, so I'll classify that as aqueous. Want to show you a little trick here. These get difficult to balance. So for the time being, I'm going to keep the water as HOH. And that's going to help me with balancing. There's this hydroxide here, and there's 2 of them because of that subscript of 2. Keeping this as HOH allows me to identify that hydroxide. And currently there's just 1 of them. So we have 1 hydroxide over here and 2 hydroxides over here. If I put a 2 out front here, that's going to fix my problem. Now we're balanced for OH- on both sides. Now I have 2 H's though. Over here, my nitric acid there's a subscript of 1, that's only 1 H. So if I put a 2 out front here, now I have 2 H's. But that gets distributed to everybody. So I also have 2 nitrates, but that's okay. There's this subscript here, which tells me that I have 2 nitrates and 1 calcium. And that corresponds with the 1 calcium over here. So now I'm balanced. And to wrap up this problem, then I'll change it back to just regular old water. That was just to help me balance it. So I'll rewrite it as 2H2O liquid. Let's do one more. We have sulfuric acid, and that splits into H+. This 2 gets sent back up here, and so I shouldn't see the 2 down here. 2 is getting sent back up there, and we have SO42-. Magnesium has a +2 charge. I know that from the periodic table. And that's that 2. Send it back to magnesium, and your other ion is just OH-. Do-si-do. So magnesium 2+ and sulfate, so -2, will form magnesium sulfate. That's aqueous. And then I'm going to keep the HOH, the water, keep it as a liquid. I'm going to balance it real quick. So hydroxide right here, there's 2 of them. Over here though, I just have one currently. If I put the 2 out front, that gives me 2 OHs and 2 H pluses. Come back over here. This 2 that came from the crisscross, well, that also means that there's 2 H's in the sulfuric acid. It's what's known as a diprotic acid. So 2H plus, that balances, and 1 sulfate. There's only 1 sulfate over here, 1 magnesium, 1 magnesium. So now it's balanced. And then I'll just fix this because it's almost a silly way to write it, but it really helps me balance. And I'll rewrite it like that.